Today we're talking about solving equations. Two different types of equations that we like to solve. Sets of linear equations in the form ax equals b, and also Newton's method, which is useful for solving nonlinear single-valued functions. Why are we doing this? Well, here's a copy of a research paper I did with a student a few years ago. We looked at using models to look at actually developing models for dynamic systems, things that happen as a function of time. So you get a lot of data, this u value for different previous value of the input, previous values of something, and you try and model response by finding coefficients a0, a1, a2, a3. When you have lots of data for this kind of model, you can set it up in this form ax equals b and get the parameters a0, a1, a2 quickly from that. Another one is a pharmaceutical problem where we were looking at powders. How do you take powders and add liquids to make granules, and look at coalescence? As you get bigger and bigger granules, they hit each other and they coalesce to make bigger particles. And one of the things we did was, again, set up a lot of models in this form, solve a problem ax equals b, and you use this inverse equation to back out the parameters of your model. This occurs all sorts of different types of engineering problems all over the world. It's not just in my research group. This is just a couple of examples I'm familiar with. So, fundamentals. In arithmetic, there are three concepts. We're doing linear algebra at this point, so we need to talk about arithmetic for algebra. We need the additive identity, a multiplicative identity, and an inverse. In scalar numbers, you know this. You've seen this before. You can add 0 to any number. This is the additive identity. You get whatever you started with when you add 0 to that number. Number 1 is a multiplicative identity. If you multiply 1 times anything, it gives you the original number, except for 0. An inverse is also another fundamental concept, where you take that inverse of a number, multiply it by the number of times its inverse is going to always give you 1. So we have the same kind of concept here. The 0 matrix, when added to any matrix, you get the original matrix. It doesn't change the matrix. The identity matrix, if you multiply by an identity matrix, we have to get a regular matrix again. And a matrix can have an inverse. So we have a special thing called A inverse, or a matrix inverse, where we get, when we multiply a matrix times its inverse, we get basically 1. So today we're talking about sets of linear equations. Here we see 3 equations with 3 unknowns. A set of 3 equations. This should look familiar for things you've done in the past. We are going to use matrix vector notation, where we take the coefficients 1, 2, 3, 5, 6, 7, 9, 1, 2, put them in a 3 by 3 matrix. You'll have to convince yourself that this 3 by 3 matrix times this 3 by 1 vector gives you this left-hand side over here. Because if you dot this row, 1, 2, 3, dotted with x, y, z, you get 1x plus 2x plus 3z. And you dot 5, 6, 7 with x, y, z, you get 5x plus 6y plus 7z. And if you dot 9, 1, 2 with x, y, z, you get 9x plus 1y plus 2z. So we have a 3 by 3 matrix, a 3 by 1 vector, and a 3 by 1 vector. In short form, or linear algebra form, you write this as a matrix A, 3 by 3, a vector x, and a vector b. Sometimes people use underlines to represent, oh, a single underline is a vector, and a double underline is a two-dimensional matrix, a matrix with rows and columns. Some people use arrows above, but that usually responds for a vector. It could have an arrow above, but that would be a force vector, and usually those are limited to 2 or 3 dimensions. Whereas these vectors, we could have a problem with 1,000 unknowns and 1,000 equations. So it makes sense to sort of, you can't visualize it very well, but you could have lots and lots of unknowns and lots of equations. Once we have these values, what do these represent? These 3 equations, if you take 2 of them, each equation represents a plane in 3-dimensional space. You can solve for z and figure out what the value of z is as a function of x and y for each of these 3 equations. So if you take 2 planes and you intersect those planes, you get a line. If you take that line and you intersect it with a 3rd plane, you're going to get a point. So once we solve these 3 equations, which represent 3 planes, we're trying to find that one point where all 3 planes intersect, if it exists. So to do that, we're going to talk about the matrix inverse. Once we have our set of linear equations in this nice form ax equals b, What can we do? Well, let's assume we have a matrix inverse matrix. So this matrix inverse, if we multiply on the left, remember we can't always move things around. In this case, we can't right multiply. Well, we don't want to right multiply. So we're going to left multiply A inverse times A and A inverse times B. But we know that a matrix times its inverse, or an inverse times a matrix, should be the identity. So this value is going to go to I, the identity matrix. 1's on the diagonals, 0's above and below. So now we have I times X, but anything times the identity should be whatever you started with. So we end up with X equals A inverse times B. X equals A inverse times B. So if we magically knew this matrix inverse, this inverse matrix value, A to the -1, and we know B, we would have everything we need to know. It's a very simple multiplication. This matrix times this vector gives us the solution. But finding this matrix is not very easy typically. Two important things. Not every matrix has an inverse. Invertible matrices have non-zero determinants. So a matrix with a zero determinant does not have an inverse. That means you can't solve that set of equations. And we're also only considering square matrices. We're not going to talk about non-square systems. That's beyond the scope of this class. Assuming you have the same number of variables as you have equations, that means it's a square system. But there are cases where you can have a matrix that has a zero determinant, which means it doesn't have an inverse, which also probably means you have badly formed equations like two parallel lines or two parallel planes that never touch each other. Or you have two planes on top of each other, so your equations are redundant. They're on top of each other and they just don't have a solution. You have many solutions. So you either have, in these bad cases, you either have no solutions or you have an infinite number of solutions. And again, we're not going to talk about that. We're going to assume that we have well-posed problems. Let's talk about a 2x2 matrix, the easiest case for a matrix. If you have a single 2x2 matrix with 4 elements, A, B, C, and D, the 2x2 matrix inverse can be written down for any 2x2 matrix. You flip A and D, AD elements flip, and you multiply B and C by -1 and divide by the determinant of A. So, we have this matrix inverse we know is just flip the A and D elements, A and D flip, B and C are multiplied by -1, divide by the determinant of A. That gives you a 2x2 matrix inverse. So if we have this formula, and we know our numbers are 1, 3, -2, 4, we can find the inverse matrix, flip the 4 and 1 elements, multiply the 3 and 2 by -1, and divide by the determinant, which is 1 times 4 minus 3 times -2. So when we do all that calculation, remember we can divide elements and multiply elements as a scalar value. So 4, this is going to be a 4 minus -6 is 10, 4 tenths, -3 tenths, 2 tenths, 1 tenth. This should be our matrix inverse. Are we done? No, because we need to check. Is A times A inverse equal to the identity? And that's easily done. You take the original matrix, multiply by the inverse. You do this row dotted with this column to get something, and that should be 1. This row dotted with this column, you dot those vectors together, and that should be 0. This first row dotted with this column, second column of the second matrix, this row and this column give you 0. This second row of the first matrix and the second column of the second matrix gives us 1. In this case, it works fine. And it should work for every case because this is the analytical inverse matrix for every 2x2 matrix. Now, how are we going to do this in general? There's probably a formula for 3x3, but it's probably a big, big mess. We're not going to do that. The general form for an arbitrary matrix inverse, at least one way of getting to it, is to set up your linear equations next to the identity matrix and use row reduction. Row reduction has some different rules. After you do row reduction, you manipulate the set of equations using individual steps to get to the point where the identity matrix is here, and whatever's on the right-hand side becomes your identity matrix, or your inverse matrix. The row reduction rules are you can multiply any row by a scalar, as long as it's not 0. You can swap two rows to reorder the equations. You can add or subtract a row from another, And you can do any of these 3 steps at the same time if you're sort of understand what's going on. So let's go through an example of this. We start with, let's not do the example yet. Let's go through, what do? You start with column 1, get zeros below the diagonal of column 1. Move to column 2 and work to get zeros below the diagonal. Repeat all the way across the matrix, all the way to the nth column. Now you should have zeros below the diagonal and ones on the diagonal. Now there's numbers above the diagonal. You have to start again with the last column, column n, and work to get zeros above that column. And then you move to the left to column n minus 1. Now we do the example. If we start out again with a 2 by 2, 1, 3, negative 2, 4. We know the analytical solution, but let's go through this route. We have 1, 3, negative 2, 4, and we put the identity matrix next to it, 1, 0, 0, 1. 1's on the diagonal from top left to bottom right. We look at this and say we want to get zeros in this position. So to get a 0 in this position, one thing we could do is multiply the second row by a half. So that means every value in this row is going to be multiplied by a scalar value of 1/2. Negative 2 goes to negative 1. 4 goes to 2. 0 stays at 0. 1 goes to 0.5. So this is now our set of equations, and we're trying to get it look like identity on the left-hand side. So we're going to try and get rid of this 1 here. So to do that, we started with this. We're going to this as a step 2. We add row 1 to row 2. If we do that, we add 1 to 1, negative 1, we're going to get 0. If we add 3 to 2, we're going to get 5. If we add 1 to 0, we're going to get 1. If we're going to add 0 to 0.5, we're going to get 0.5. So that's our second step. So we have almost gotten 1s on the diagonal. We've gotten 0 below. We've gotten 1s starting on the diagonal. We've multiplied the second row by 1/5, all the elements by 1/5. We replace that row 2 with 0 times 1/5. 5 times 1/5 is 1. 1 times 1/5 is 0.2. 0.5 times 1/5 is 0.1. So now we have this set. We have 1s on the diagonal and 0 below. This is pretty close. We basically solved the problem at this point, but we want the matrix inverse, which has a specific meaning. So we take this value, our set of equations. Now it gets tricky. You have to do 2 steps at once. We're going to subtract 3 times this row from row 1. So 3 times row 2 from row 1. So we want to get rid of this 3. And the only way to do that is to do 2 steps at once. You have to multiply this row by 3 and subtract it from row 1. So 3 times 0 from 1 is 1. 3 times 1 from 3 is 0. 3 times 0.2 from 1 is 0.4. 3 times 0.1 from 0 is negative 0.3. Now we have the identity matrix here, and whatever is here is A inverse. So now that we have A inverse, what do? We check. We started off with 1, 3, negative 2, 4. We multiply it by 0.4, negative 0.3, 0.2, and 0.1. That should give us the identity 1, 0, 0, 1. Now, you may think, why don't you just divide? Well, it's just not defined. You can't do that. It's a math thing. With matrices, you cannot divide one matrix into the other. But you can multiply by an inverse, as long as the matrices have the right dimensions. Again, why are we doing this? If we have sets of linear equations, there could be lots of variables, lots of equations, and they're all linear, where you have a constant value times a variable, plus a constant times a variable. And this often occurs when we're solving numerical problems. It's easy to solve analytical problems where you have simple algebra and you can find the solution for all cases. But if you have numbers on the coefficients and you don't need it in terms of variables, you have to actually come to a numerical solution. You can have to solve a large set of problems, like this example from ComSol, or these fluid flow problems. You look at setting up sets of equations, and the computer automatically sets up and solves lots of AX equals B type problems. What about nonlinear equations? That's another thing we need to talk about. Y equals f of x. So your mathematical equations can represent the system. And the roots of the equation are the solution, where what values of x satisfy this equation. That gives you a solution. So like y equals 3x can be written as the form y minus 3x equals 0. So what's a root? Where does this value go to 0? So we can describe the response of y as it changes in terms of x. And this response can be linear or nonlinear. A lot of real systems are nonlinear, and a lot of models we use for those systems are nonlinear. So some examples. If you're dealing with kinetics, how fast things react in the presence of an enzyme, there are often nonlinear reaction rates. So the reaction rate for a chemical reaction in a biological system may be a nonlinear dependence. It's not just a constant times a concentration variable. It could be a constant times a concentration variable squared, or some power law, or some denominator term. So it's not just a simple constant times a variable. It's more intricate than that. If you have populations of cells, there are nonlinear motion equations used to model these types of processes. Heat transport. You can have nonlinear temperature property. The physical properties of a process may depend on temperature. So things like viscosity and density may change as a function of temperature, and that makes all of the equations you're trying to solve nonlinear. And flow. When you're flowing things, there are not all sorts of nonlinear effects when you have liquids or gases flowing around in a system. It's just lots and lots of complex models arise when you start to make things more and more nonlinear. For linear equations, we know how to do this analytically. If we have an equation in the form y equals mx plus b. So f of x is a linear function of x, where we have a slope and an intercept. If we have an actual example with numbers for the slope and numbers for the intercept, we can plot this and find that root, find the solution to that equation. We can do it analytically if we only know y equals mx plus b. We want to find where y equals 0. Well, we can solve that equation. Well, if y is equal to 0, you bring the b across and divide by m to solve for x. When you do that, you know that x is equal to negative b over m. That's an analytical solution for every value of b and m. Now, if you have numbers for b and numbers for m, you can plug into the analytical solution and find the numerical solution. So the numerical solution is actually 1.5. For quadratic equations, ax squared plus bx plus c, you know the solution is the quadratic formula. We can determine this analytically because we have the quadratic formula. And there are formulas for higher order polynomials as well. So for a given polynomial with actual coefficients, we plug in the quadratic formula and we get two solutions. Oh, look, there are two solutions as expected. The general polynomials have a more complex form, where an nth order polynomial has n plus 1 coefficients. We have a constant value, we have the linear term, we have the quadratic term, and then we go all the way out, all these a values, up to an minus 1, an. These are all polynomial coefficient models. We cannot always determine these analytically. Again, for higher order polynomials, you can't find them. But it's very trivial. If you have numerical values for the polynomial, we can find the roots of this equation trivially in MATLAB. So let's consider a single general nonlinear equation. So if we have g of x equals h of x, we want to find what values of x make these two functions equal. Let's rewrite this by pulling h across. So g of x minus h of x equals 0. Or we can write this in the general form we usually see, f of x equals 0. Now the iterative Newton's method is just take your value of x, subtract this update or change, the value of the function at the current value of x divided by the value of the derivative of the function at the current value of x. So if you know x and you know the function and you know the derivative, you can use this simple update formula to get the next value of x. Newton's formula is very simple. You've seen it in calculus ideally. Let's do a little graphical example. What's actually going on? We want to find f of x 0, where we have this function crossing the 0 line. So if this is our y equals f of x, at some value of x, the function of x is this value above 0. And the derivative just defines what this plane is, this line, tangent to the function at that point. So we use the Newton's value formula to find, since we can do it analytically for a linear system, we can find this solution right here analytically for x equals 2 for the second iteration. So once we have that slope and we want to have that function evaluation, we find x2. We take that function for our next iteration after solving these functions analytically, this nice linear function, and we can solve for the next value. So we basically say f of x is this value. We know the slope. Let's make a line out of that. We can iterate for a third iteration. And after 1, 2 iterations, we're actually pretty close to the solution. 3 or 4 iterations would get us there very quickly. But you have to know the slope and the value of the function. At each point, you have a starting point, figure the function value and the slope, and plug it back into this update formula. So, in general, your solutions could have more than one root. The closest root is typically the one that you find. So when you start with an initial guess, we look for a local root that satisfies the equation. So for this simple example with x cubed equals natural log of x plus 3, we bring the function over here, we get x cubed minus natural log of x minus 3, and the derivative of that is this guy. So if we start out with an x value of 1, we plug that into this function, and we plug that into this derivative function, we get negative 2 and 2. So the next value is going to be 2, ironically. We stick that in here. Our x value becomes 2. F of x and f prime of x evaluated at x equals 2, 4.3 and 11.5. When we plug these two values, x, f of x, and f prime, into this function, the Newton's method function, we get 1.63. So our next value of x is 1.63. So when we have x equals 1.63, we plug that into the function, the derivative function, and we plug those two values in here, and we eventually get to 1.52. If we evaluate that in the function, it's pretty darn close to 0. It's not exactly at 0, but the function started at negative 2, and it went further away, and they got to 0.84 and then 0.09, another iteration, and we'd be very, very close to 0. Now, just to sort of remind you, why are we doing this? We have two different types of models we can solve now. They're model equations, and we have to solve these equations and know the different tools to solve these equations. So the basic way to solve these equations depends on what the equations are. So if you have a single nonlinear function, a scalar value, you have a single variable and a nonlinear function, you can use Newton's method. If you have lots of equations and lots of unknowns, you can solve it using ax equals b linear algebra methods. So again, a scalar function could be f of x equals 0 or f of t, where you're plotting some value versus t and you want to find where that value goes to 0, or you can have some value like the voltage. Find where the voltage as a function of time is equal to some value. So all of these values, you don't know what value of x satisfies this equation or what value of t satisfies these equations. You can solve those using Newton's method. If you have linear equations, linear values, you can set up in the form ax equals b, and you find the matrix inverse to solve for x equals a inverse b. You could also just solve for one variable and plug it in the next equation, solve for a variable and plug it in the next equation. That gets tedious. I want you to understand the reason we use this matrix inverse for large sets of linear equations and how to find the matrix inverse for simple problems. There are vector nonlinear functions. So you could imagine like a function of the equation for a circle, the equation for a parabola. These are functions of x and y. And you could set this up to try and solve for the points where this equation and this equation are both satisfied. It's again, beyond the scope of this class, but basically it's a Newton's method where you solve ax equals b at each step. Instead of a simple linear solve, you have a simple multivariable linear solve for each iteration. But we're not going to talk about that. Just realize you could solve sets of nonlinear equations in special cases with the right kinds of methods. And again, why are we doing this? Here's another research paper with some graduate students where we had these types of nonlinear functions. We're trying to find solutions to this problem. How do we find the values that give us, how do we run our reactor for our system by changing flow rates so that we get to the desired set points? And here's one with a student looking at a biomedical problem where we were looking at control. We have diabetic patient insulin delivery. So we have a model and we're trying to figure out how much insulin to give to that patient. We set it up with a special type of Laplace transform model, which looks like a lot like a polynomials we've been talking about. And you have to solve for the roots because that determines stability of the system. Do you blow up your patient or kill your patient by giving too much insulin or not enough insulin? And that depends on how you set up the system. Thank you very much for your time.